This chapter will act as an introduction to graph algorithms. We will be addressing terminologies, applications, and representation, each in a separate section willing to make it easier to track. In this section we will be handling some basic concepts in graphs, starting with a comparison between directed and undirected graphs, moving to adjacent nodes, path and simple path, explaining loops, cycles and simple cycles, digging deeper into weighted graphs, complete graphs, and ending with subgraphs. The next section will introduce more concepts. Now, before we start explaining graph concepts, we must be familiar with graphs themselves. So, consider a graph G. Any graph consists of set of vertices, can be referred to by nodes or points. Also, it contains a set of edges called arcs or lines. In this graph, C is considered a node. BD is an example of an edge. Can you tell how many nodes and edges in this graph? Here we must notice the relationship between nodes and edges. In any graph, the number of edges must be less than or equal to the number of nodes. Keep that in your mind, you will need it later. Now we will start our way through better understanding. We will begin with directed and undirected graphs. This is an undirected graph. It consists of 4 nodes and 4 edges. Can you name the nodes and edges? The nodes are A, B, C, and D. The edges are a B, a C, a D, CB, beer, seer, deer, BC. Note that the edges are not directed. No arrows are used, hence, edge BC is the same as CB. As for directed graphs, they also consist of nodes and edges, but these edges are directed. They are called sometimes diagraphs. The nodes are A, B, C, and D. The edges are a B, a C, a D, and CB. Having an edge, C, B, does not mean that BC exists. Meaning, edge CB is not the same as edge BC. Now moving on to adjacent nodes. Adjacent nodes are those connected with an edge. See the following graph. Node A is adjacent to node E, as well. Node E is adjacent to node A. So, in undirected graphs, any 2 nodes connected by an edge are both adjacent to each other's. Where in a directed graph, E is adjacent to A, but A is not adjacent to E. Can you say why? Since the edge E isn't the same as EA, only the destination node is adjacent to the source node. Next we will talk about path and simple path. A path is a sequence of edges between nodes. It is like a route or a way. Follow the following path, B, C, D. It connects node B with node D. There is a special kind of path, called simple path. A simple path is a path where no node is visited twice, except for the first and last nodes. Check this path, B, C, D, B, C, A. Note that the nodes B and C are visited twice, therefore, this is not considered as a simple path. We can find out the length of the path by counting the number of edges in the path. The first path is 2 edges long. The second path length is 5 edges. We will address loops now. A loop is an edge from a vertex to itself. This is a loop. We will be studying only loopless graphs. Moving on to cycles and simple cycles. A cycle is a closed path. It ends from where it started. Let's look at the following example: B, E, C, D, B. This is a cycle in a digraph. It must be at least between two nodes. The first node must be the same as the last one. If the path is simple, then so is the cycle. Consider the following example: B, E, C, B, D, C, B. What do you think? It started and ended with the same node, so it is a cycle. And the nodes are not distinct, they were visited twice, so it's not a simple cycle. How about the length of this cycle? That's right, 6 edges. Undirected graphs also may contain cycles. They must be of length at least 3. Now, track the following: A, C, B, A. That's a simple cycle. Where the following: E, C, A, B, C, E is not a simple cycle. We will have a brief exercise now trying to make it clearer. Consider the following and decide if it's a path or a cycle. 1. B, D, C, E. This is a simple path. 2. G, F, B, A, G. Represents a simple cycle. 3. E, C, B, A, G, B, C, E. It is a cycle. Now we will move to weighted graphs. A weighted graph is any graph that carries a value. G consists of vertices, edges and weight. This number may indicate distance, and nodes represent cities for an example. We reached complete graphs. In a complete graph there is an edge between each pair of nodes. It is all possible edges. See the following examples. It can be one node, 2 connected nodes, or as many as you wish but with an edge connecting each pair. We will end this section with subgraphs. A subgraph is a subset of nodes and edges that forms a full graph. We can obtain this subgraph from G, or this one. But is this a subgraph? Why? It is to be a full graph. This one misses a node. This is the end of this section. The next one contains some more important concepts. Welcome. This chapter will act as an introduction to graph algorithm.